This is not something you don't think about for a while yet, but I guess it's a better time before the semester's over, thank goodness. The last full month will be upon us soon. So someone started thinking about, there's two options for the final. So either an oral final exam, which some of you might have done in the past, in upper classes, where I could ask about whatever concepts we covered, kind of like a quiz questions in a way. I wouldn't be asking you to spit out MATLAB code orally, or there's a coding option, and that's already posted on the assignment page. So it's up to you. Pick your poison. Just let me know. And then if you want the oral option, then we just need to figure out the scheduling of it. And sometime around finals week, or it could be a week before. This is where everything stops. This is the Thursday of finals week, May 12th. So we'll have everything in by then, so that I can take the next few days to get everything graded for the grading. The deadline to submit final grades is following Monday, the 16th.
So, like, if we were to do the oral option, will there be any kind of guide on what to study, or would it just be like the concept checks?
Concept checks are the best guidelines I can give you there.
Mm-hmm.
Yeah.
Okay.
Like for instance, properties of certain methods, what are advantages of one kind of method over another. Like we're about to see methods on ODEs. There are several methods that we're going to see. And certain concepts related to them, like for instance, root finding methods. What do I mean by order convergence? For methods for ODEs we're about to see, we're going to see important concepts like consistency, stability, convergence. What do those mean? Do you have a term straight? Things like that. So, can he be conversant in these topics? Okay.
I just heard conversant first, and I was like, yeah, I could talk. I don't know.
Not too many people choose the coding option. That always seems to be the greater evil compared to whatever else I put out there. But there's only 6 of you, so we'll have much to grade in any case. At least with the coding option, I've included like a framework, including a testing script, so that lets you see before you turn it in whether your code is working. All right.
You said it's uploaded then?
Oh no, I mean, actually, you know what? I don't know if I put it in Canvas yet. Let me check.
Oh, okay.
Okay, there's something here. Oh, I didn't put the info here. On my external site here, you can see everything. But yeah, oops. I need to get that same info into Canvas. So I'll do that shortly. That's quite good. Last time I taught this class, that was the very first semester of a pandemic. I think I would have put that in here, but oh well. Okay, so the info's out there, and I'll make it more accessible soon. Okay, so the rest of the way, we're dealing with ODEs. First, initial value problems. So this is the general problem we'll be working with. The y prime is some function f of t and y on some interval in time. Usually the initial time 0, just for convenience. And then we have some initial condition. All right. Now, you would know how to solve at least certain initial value problems from a typical first course in ODEs, like our Math 285, for instance, or whatever equivalent if you weren't here for your undergrad. And for first order equations, you would learn about certain methods. Or if you were able to classify a first order ODE as being of a certain type, then that would indicate the solution method to use. Do you remember what those kinds of equations were, or what kind of solution methods? Anyone? For some of you, it may have been a while.
Say it one more time.
Like ways to certain types of differential equations that could readily be solved, or approaches to solving them.
No.
Something went completely dumb.
Explicit. Explicit.
That's actually going to come about for numerical methods.
Yeah.
I thought analytical methods from a regular math class.
Oh shoot.
Well,
Something boundary up.
I know you'd find the characteristic something. Now.
that's for higher order equations.
Is it Laplace
What? Sorry?
transforms? The Laplace transforms?
Well, plus.
Yeah, plus.
Well, yes, that is one. Okay, so that's one example that can be used for first order or higher order ODEs. Any other? I guess a little fresher in your mind than others. I guess that would have been covered at the end of a semester, so.
Yeah.
I didn't realize how long it's been since I thought about just a regular ODE.
Yeah. Okay. So I'll give you an opportunity to kick yourselves. For example, if the ODE can be classified as separable,
Right.
then you can rearrange it and integrate both sides. Or if it is a linear equation, you can use what's called an integrating factor. So certain ODEs can be classified as exact, which is a sort of generalization of we also call for integrating factors. So certain ones can be classified as homogeneous. So here's the good part, though. To understand and use numerical methods for solving ODEs, you don't have to remember any of that stuff. We're not going to use one little bit of it. Now, since you mentioned that it's been a while since you've taken that, I actually never took a first course in ODEs. Wow. Nor did I test out of it either. It is one of those things where so for my undergrad at Purdue, there was a course that was differential equations and linear algebra together. And then I took an honors version of that, but that was just linear algebra. For other classes, like there was a second course in differential equations that was more theoretical, and then also a first course in PDEs that is similar to our 417, 517. They let me take those, even though I did not have that one prerequisite. I'm not sure why. And then when it came time for graduation, they noticed like, oh, I've never taken this. And so some professor just signed something and said like, oh, he's gone beyond that. There's no need to make him take it or something. So I just skedaddled without ever taking a class. And then I think it was 4 years later was when I was an instructor at Iowa State, and I had to teach that. So I was assigned to teach that. I was like, well, I guess I better learn this stuff now. It did not go very well. And I've taught it a few times here. So that's one way to learn, I guess. But yeah. And it does come in handy for a lot of things. Like certainly the various higher level or graduate classes that deal with ODEs or PDEs, that we often build on that. And in some cases, it plays a role with numerical methods too, but for this beginning stuff, not so much. Okay, now, I guess one thing I'll mention about this general initial value problem. So making a reasonable assumption on f, the function that defines the time derivative, and I'll tell you what that assumption is, satisfies a Lipschitz condition in y. So in other words, f of t y2 minus f of t y1, notice the same value t in both cases, is bounded by some constant L times y2 minus y1 on some domain that I'll call D. All right, so if f satisfies this kind of condition, then this initial value problem is said to be well posed. And what does well posed mean? A solution exists, the solution is unique, and it depends continuously on the data. Meaning that a small change in f or small change in the initial value does not cause an unduly large change in the solution. That's important for numerical methods because generally problem data fed to a numerical method is erroneous. If some tiny error, like round-off error, could substantially throw off a solution, then that's a problem that cannot practically be solved numerically. And once in a while, that does happen. Not anything that we've seen in this class or last semester. It does come up in a problem I cover in Math 610, the numerical linear algebra, where a slight change in the problem data can cause an abrupt change, like an entry that a matrix that should be 0 will suddenly become 1. So that's a big jump. That's an example of a problem that is ill-posed. It does not depend in a continuous manner on the initial data. So most, normal problems generally are well-posed. So here I'm under this reasonable assumption about the continuity of f. Equivalently, if the derivative of f, partial derivative of f with respect to y, is bounded on a domain, so it's less than or equal to this Lipschitz constant L, then that's equivalent to this condition in a case where the first partial derivative of f with respect to y exists. Then we have that's well posed. So this relates to what's known as the existence uniqueness theorem that is sometimes covered in first ODE courses. So in other words, under these circumstances, this is a problem that is numerically tractable, that is feasible to apply a numerical method to. Okay. And it's worth mentioning that I'm not going to get into a proof of this because it's not that kind of class. Although when I do come for proof in the ODE class, I can just sense how the pain of the students, like they can't stand to sit through this thing. So at some point I stopped doing it just to show some mercy. But I was kind of sad about that because it is a pretty cool proof. Well, I guess Dr. Tian covered it in Math 605, I believe.
Yeah, I think we might have.
Yeah, it's
our presentation.
Yeah, I think it's what it was. Yeah.
Yeah.
It's a big old proof. There's a lot involved in it.
It is.
Theory of fixed point iteration. Applied to solve this equation, yt is equal to y naught plus the integral from 0 to t of its time derivative, which is f. Yes, because here we have y of t here, and then y of t inside the integral. So this you can think of as a function g of y. So the argument of g is a function. So you show that this is a contraction, and therefore the iteration involved, you solve this equation, will converge. So all the theory about fixed point iteration that I was showing you recently is now applied here. So it's interesting how all these different areas of math, but also numerical methods, overlap. All right. Okay. So now that we know that this is a problem that can be solved, how do we go about solving it numerically? Especially if we're not going to bother with kind of analytical methods you learned about in a class like Math 285. So today, I'm just going to cover the simplest method possible. And then later on, like on Monday, I'll start getting into more elaborate methods. Okay, so in general, here's how numerical solution of ODEs works. We're talking about initial value problems. And I have to make a distinction because here, this chapter we're starting now, chapter 12, is all about initial value problems. After that, I'll finish the semester covering some of chapter 13, which is on boundary value problems, still for ODEs. In that case, a second order ODE, where you have boundary conditions specified at two endpoints of an interval. So still about ODEs, but of a very different kind. Now, when you're solving an initial value problem of this form, and we're sticking with this form because suppose you have a higher order ODE, like second order. You can write it as a system of first order equations. You can always do that. So if you have like a second order ODE can be written as a system of two first order ODEs. And the numerical methods I'll show you, I may illustrate them for being applied to a single ODE of this type, but they apply readily to systems of ODEs too. And you may not even have to change your code at all. Okay. So the idea is the following, and this will give you a chance to introduce some important notation. We're not going to compute a formula for a function y of t, like you would in using an analytical method. We're just going to compute the approximate values of y of t at selected points. So here's my notation. This here, y of tn, represents the exact solution at time tn. And my time values, t1, t2, etc., are equally spaced values in time, and the spacing between time values is h. So I'll use h to refer to the time step. Now, as I just said, we're assuming a uniform time step here. We don't have to assume that. There isn't such a thing as adaptive time stepping, where you change the value of h. You can make it smaller or larger. For instance, if you find that the solution is very well behaved, maybe you can get away with a larger time step. But if it's more oscillatory as opposed to smooth, you might find a need to use a smaller time step. So all the methods that I'll show you can be modified to perform adaptive time stepping. I'm not going to get into that. There is a section for that in the text, in section 12.5. But we're not going to get into that in this class. So for our discussion, we'll assume a uniform time step. So what we're going to compute are, we have our initial value y0 that's given. So we're going to compute y1, y2, y3, and so on, that are approximations to y of t1, y of t2, y of t3, etc. Now, what you're going to see in this chapter is that there are many different ways of classifying time-stepping methods. There there's one step versus multi-step. There's explicit versus implicit. And these categories all overlap. So I'm going to start with one-step methods and also explicit, and then I'll talk about implicit later on. And then we'll get into multi-step methods. So what do I mean by a one-step method as opposed to a multi-step method? So in a one-step method, you've time-stepped from t0 up to tn. Computing solution values y1, y2 up to yn. Now you want to get yn plus 1. So in the one-step method, you compute yn plus 1 using only information gathered from this interval, from tn to tn plus 1. In other words, whatever happened with the solution earlier, you forget about it, which is convenient from a storage point of view. Although one could argue it's not very efficient to just forget all of that. Multi-step methods do use earlier information. So you might compute the solution at time tn plus 1 using information from time tn, tn minus 1, tn minus 2, tn minus 3. For a multi-step method, you figure out how far back you want to go, and then you do that with each time step. And that can be more efficient, although it's a bit of a pain because you can't do that in your first time steps. If you're going to go back a certain distance, but if you're about to take your first time step, all you got is t0, y0. You can't go back further than that. So you always have to use a one-step method at the start, and then your multi-step method can kick in. All right. So how do you design a one-step method? You can use Taylor expansion of the exact solution. So I use that now to derive the simplest time-stepping method. So here's Taylor expansion of y of tn plus 1, and the Taylor expansion is centered at time tn. So if I just take the Taylor expansion out to the second derivative term, then this is what I have, where c is some unknown point that lies between my center and my evaluation point. So then what I can do is, since this is, what we have here is exact, so now, if I neglect this term, which is order h squared, and if h is small, then this term is especially small, then I have an approximation. So that's what Euler's method is based on. Now, again, keep in mind, y of t is the exact solution, whereas y with the subscript, that's my computed solution. So my approximate y at time tn plus 1 is the approximate y at time tn h times the time derivative at time tn. So this comes from neglecting the this term in the Taylor expansion. You see that everything else matches up. So that's called Euler's method, the simplest time-stepping method of all. Which actually might be taught in at least certain first ODE courses, depending on the instructor's preference. So what we want to find out is, does this method actually work? And I have to define what that means. What does it mean for a time-stepping method to work? And here's how I define that. That the computed solution must converge to the exact solution. So if I'm letting my time step go to 0, and I consider all time steps from time t naught up to time capital T, which is my final time, and I look at the error, the difference between my exact solution at each time minus my approximate solution at that time, that the maximum error must go to 0 as the time step goes to 0. So when this happens, we say that the time stepping method is convergent. So that's the goal. Come up with a time-stepping method that is convergent. So now what I'll do is prove that Euler's method is convergent. It's going to be a pain. So what I do is I compare what's happening with a computed solution as opposed to the exact solution. For the computed solution, we have Euler's method. This is how y plus 1 is defined for Euler's method. Whereas for the exact solution at time t n plus 1, for that I have a Taylor expansion that I've written out here, same as before. Now, we assume we're dealing with a well-posed problem, that f satisfies this Lipschitz condition in y. Otherwise, we probably shouldn't be using a numerical method in the first place. Or, well, the problem, again, it's an ill-posed problem in that case. There's likely no hope of solving it. Now, as a shorthand, I'll define En to be the error. Computed solution minus the exact solution at the corresponding time. So then what I can do is subtract these two equations and see what I get for a relationship between the error after n plus 1 time steps versus the error after n time steps. And this is what I have. So here I have new error equals old error plus h times the difference in these f values. And then I also have this second derivative term here. Here is where I take into account that f satisfies a Lipschitz condition. I'll also assume that the second derivative is continuous on the interval in which I'm time stepping. That's important because then I can assume that the second derivative has a minimum and a maximum. So that's what lets me assume the existence of some upper bound here. So now, because f satisfies the Lipschitz condition in the y argument, this term here is less than or equal to h times the Lipschitz constant L times the difference in these y values, which is En. Now I have 1 plus HL times En. So new error is bounded by this factor times the old error. And then I have this term here that I can bound by h squared m over 2. So in other words, I have a recurrence relation for the errors at the various times. Questions up to this point? So now I apply this repeatedly, because I can use a recurrence relation to express En in terms of En minus 1 using this same relation. So that's what I do here. So what's in these square brackets, En is expressed in terms of En minus 1 using this relationship. And then I express En minus 1 in terms of En minus 2, again using this same relationship. So just going back a couple of steps, if I simplify this now as much as I can, over a course of 3 time steps, I have En plus 1 is bounded by 1 plus HL cubed. So the 3 here represents the number of time steps I'm considering. And this is the error from 3 time steps ago. And then what do I have here? All of these other terms have this common factor of h squared m over 2. And then look what I have. A sum of powers of 1 plus HL. So the 0 power to the first power to the second power. In other words, this value minus 1. So I can continue this process all the way back to time step 0 where I have initial data. So En is bounded by 1 plus HL to the n times the initial error. and then I'll have this h squared m over 2, and then I have a sum going from 0 up to n minus 1 of these, of 1 plus hl to these powers. But this is the error in the initial data. Well, we have the initial value exactly. So E0 is 0, so this part just goes away. And then, for this part, this is a geometric progression. I have a formula for this. So this is equal to 1 plus hl to the n minus 1 divided by what's being raised to the i's power minus 1. So in other words, hl. So I actually have an hl in the denominator. The h down below cancels with one of the h's upstairs. And then I have this factor of capital L in the denominator. So it all simplifies to this. So questions about how this expression, this upper bound, was arrived at? There's a bit that I glossed over, but I made sure to at least talk about each piece. Oh, actually, here's a formula that I used, the sum of the first terms of a geometric series. This formula is what gave me this. Now, 1 plus x is less than e to the x when x is positive. You may recognize this as the first two terms in the Maclaurin expansion of e to the x. The terms that are left out are also positive when x is positive, so we know it's strictly less than. So I can replace this by e to the hl. That means I'm going to have e to the h times l times n. And I'm replacing this with exponential because it helps me do something with this exponent of n here, because h times n is the difference in times, Tn minus T naught, which is certainly less or equal to the final time minus the initial time. So here's the bound I had before. But now, this simplifies to e to the L n h, but n times h is bounded by the length of your time interval, and now I have this bound for the error. But I want to see what happens to this error bound as h goes to 0. Well, I have this factor of h sitting here. Everything else is a constant, independent of h. So as h goes to 0, it's easy to see the error goes to 0. So we can conclude that Euler's method really is convergent. What's more, because the error is proportional to h, that means that the error is big O of h. It can be bounded by a constant times h. So this method is said to be first order accurate, as opposed to higher order accurate methods where the error might be order h, big O of h squared, big O of h cubed, which is what we prefer. So this is not a great method by any means. It converges slowly compared to other methods that we'll see, but at least it does converge. And we know that this is the error. This is the simplest time-stepping method we got, and the proof is still pretty cumbersome. Fortunately, we'll introduce certain concepts that will make it easier to prove convergence for other methods that we'll learn about that are more elaborate. I should also point out that we're just looking for a bound on the error to prove convergence. This is definitely not a sharp bound at all. So here we took an upper bound because of Lipschitz condition. Also, this is very crude upper bound, 1 plus x less than e to the x, because e to the x grows a whole lot more rapidly than 1 plus x. So this is very conservative, but we're okay with that because all we're trying to do is prove convergence. That the error goes to 0 at all. Any questions about how this concluded? Alright, so comments on the error bound. Okay, so I already mentioned that it's not a sharp bound. Alright. But the other thing is, I've not accounted for round-off error in this bound. So when I say that the error at time 0 is 0, that's not necessarily true. Like, for example, suppose you're trying to solve an initial value problem, and you're given that the initial value, y0, is pi. Well, you can't represent pi exactly in a floating point system, or any other irrational number for that matter. So there is some error in that case. So that's one important simplification. Now, I don't recall, I don't think I assigned this problem. Let me check. Okay, I did not. So I'm going to take a little time to show you. All right. So here's how you take round-off error into account. So this is Euler's method. So this part here is Euler's method repeated, and we have these tilde values, y tilde, y plus 1 tilde, and this accounts for rounding error. And we assume that this error is order u, where u is a machine precision or unit round-off, which is something I covered a long time ago in last semester in 465-60. So it's the it's about the relative error when representing a number of floating point system. So if we use this model to represent the computed solution, in other words, evaluations of f are not exact, and we even have this error in the initial data, so it's delta naught, then we have a similar error bound, like this hm over 2l was present before, and we have this factor also is repeated, but we have this troublesome factor, delta over h. We want the error to go to 0 as h goes to 0, but as h goes to 0, we have this term that's increasing. So really what you want to do is you want to take this term and try to see what is the value of h that makes this as small as possible. And that depends on how large the second derivative is, because you're neglecting that in your method. And also how much error have you incurred in evaluating f. Now you may not be able to get a handle on how big this is. You can try ballparking it based on what f does. And you could try to find the minimum of this as a function of h and get an idea of what an ideal time step size is. It's like we saw last semester with numerical differentiation. I would show you an example in MATLAB where we're using the finite difference formula to approximate a derivative. And as I would decrease h, you see that the answer approximation was getting more and more accurate, up to a point and then as I kept decreasing h, the error started increasing and it got crazy. So it's the same thing going on here. So in light of what we saw from numerical differentiation, this should not actually be a surprise. So unfortunately, we can't ignore that. But we also see that the results of previous error analysis are included here also. We just have these extra terms that come about from including round-off error. And besides, even without the influence of round-off error that we see here, you don't necessarily want to use a tiny time step to solve your ODE. So can anyone give me a reason why, there's really two big reasons why we don't want to use a tiny h. The first is because, as this analysis shows, the error will grow if h is too small. What's another practical reason not to use a tiny h?
More iterations, you have to do more calculations.
It's not efficient. So using an excessively small h hurts you in terms of accuracy and efficiency. So people said steer clear of it for that reason too. All right. And I've seen this with other time-stepping methods where I'm doing a convergence analysis just experimentally. I see, okay, I expect the error to be a certain order of accuracy, or the method to be a certain order of accuracy, and I see how the error is going to 0 as h goes to 0, and it's matching my theoretical expectations. But at some point, once that error gets small enough, then it's no longer going to 0 at the same rate, or maybe not going any closer to 0 at all. Now, at that point, the error is already quite small, like on the order of 10 to the minus 12 or something, so I'm not too worried about it. But it just goes to show that once the h gets small enough, because our theory doesn't take everything into account, there's always a point at which it doesn't hold anymore. So you have to be careful about that. Okay. The other thing I want to point out through this example, so here we have a very simple ODE, y prime is minus y, and we know what the solution to that is. This is e to the minus t times the initial value. So suppose we want the error to be below a certain threshold. So if I'm time stepping from 0 to 10, I'd like to find h so that I can be guaranteed that the error is less than 0.001. Well, I have this error bound. So what I can do is I can fill in my particulars here. For this problem, I know what m is, I know what l is. I can fill in my time-stepping parameters. And I get this as the upper bound of my error at time 10, my final time. So I can take this equation and set this less than my error tolerance, which is 10 to the minus 3 in this case, and solve for h. And I get a pretty small value of h. So 9 times 10 to the minus 8. So what this is telling me is if I use h that's small, aside from round-off effects, I can guarantee that the error by approximate solution will be less than 10 to the minus 3. But if I really do apply Euler's method with that tiny a value of h satisfying this condition, my error will be less than 10 to the minus 3. In fact, it will be a whole lot smaller than 10 to the minus 3, be under 10 to the minus 11. And the reason why is this is a terribly crude bound. So it's the opposite of a sharp bound on the error. It's way too conservative. And this is where adaptive methods have their own way of estimating the error in order to give guidance on choosing a time step to keep the error below a certain threshold. So the time step suggested by that approach would be more reasonable than taking this many time steps to solve such a simple ODE. So this kind of error analysis is helpful for determining whether a method converges, and if so, what is the order of accuracy? What is the power of H? So that you know the rate at which the error goes to 0. But that's about it. It's not helpful for suggesting a practical value of H. Any questions about what happened with this example? All right, I want to take a little time to talk about how you go about solving ODEs in MATLAB. So I'll do a demonstration in MATLAB for that. All right. So here's the simplest usage of one of MATLAB has several ODE solvers. This is just one of them, called ODE 2.3. The numbers indicate the order of accuracy of the time-stepping methods that the ODE solver uses. So in this case, it's using two methods, one as second order, one as third order, using them in combination. And using two methods like that is helpful for adaptive time-stepping that all of these solvers use in order to compute a solution over a certain time interval that is sufficiently accurate with as little work as possible. So here are the arguments. A function handle f that defines the ODE, it's a time derivative. A row vector indicating the initial time and final time. So you're specifying what this interval is. And then the third argument is your initial value. Now, if you want, you can specify a vector of times that needs to be increasing. And then the output will include a solution at all of those times. If you just leave it as initial time and final time, then the output will be a vector of time values that it chooses according to its adaptive time stepping scheme, and then the corresponding solution values. So I'll show you how this is used for a particular ODE. The interval from 0 to 10. So I'll define my function f as a function of t and y. And so just whatever I have here, in this case, minus y. So it may not use t, but the ODE solver will assume it's a function of these two arguments, so you have to list them here, even if you don't use them both. Okay. Then my initial value is 1. My time span consists of my initial time and my final time. Okay. All right, so now I can do this ty, my outputs, time values, solution values, is ODE 2.3, f, t span, y0. All right. So now my time values is a column vector starting at time 0 and stepping all the way to time 10. Now to show you what time steps were taken, I'm going to use the diff function And we see that at first time step it took 0.08, then through its error estimation it figured that it could get away with a larger time step, so it increased it h to 0.2989, but increased it a little further, and it stuck with this for quite a while, and then found it could increase it even more. So that's Malin's adaptive time stepping that's happening behind the scenes. And then the corresponding y values are given here. So the exact solution is e to the minus t. So starting at the initial value of 1 and slowly but surely exponentially decaying from there. So what I'll do now is I will plot. Okay. So first I'm going to plot the exact solution against the t values that it gave me using a blue solid curve. Okay. Always label your axes. Okay, so that's my exact solution. So now I'm going to plot t gets the computed y values. Now I use red circles for those. And sure enough, they coincide. At least to the extent that we can see on the plot. But since I know the exact solution in this case, I can also do a legend. Exact, which is because that's the first thing I plotted, and then my computed solution. And that puts a legend right here in the corner. I'll post this plot in Canvas. All right. If I want to know the error, I could use the norm of my y values minus the exact solution values. And I'll take a relative norm. So a relative error, that's pretty small. So 8 times 10 to the minus 4. Right, so that's pretty good. Now, if you look at how I use the function, ODE23, here it is. Here I'm solving a single ODE. If I'm solving a system of ODEs, which might happen, for instance, if you're wanting to solve a PDE, you discretize the PDE in space first, and that gives you a system of ODEs, which you can solve using solver such as this. Your function f for a system of ODEs would take in arguments t and y would be a vector, and the function f would return a vector of the same length. The initial value, y naught, would also be a vector. What happens in that case is the output y is now a matrix. Each row of the matrix is the solution at a certain t value. So for instance, the 10th element of t is the 10th time at which it computed a solution. And the 10th row of this matrix y will be a vector consisting of a solution at that corresponding time. So if you want to solve like a second order ODE, for example, you rewrite it as a system of 2 first order ODEs, and then you define your function f to be the time derivatives, return time derivatives for both those ODEs. So f will be a function that takes in a vector as a solution, returns as output a vector of 2 elements. And since a second order ODE requires 2 initial values, y of 0, y prime of 0, then your y naught would be a 2 element vector consisting of those 2 initial values for y and y prime. So questions about how you solve at least a simple ODE in MATLAB? In this case, because the ODE was particularly simple, I just defined f to be an anonymous function like this. But for something more elaborate, I could easily write a function in an M file, and that's when I would pass the first argument to my ODE solver. I want to point out for systems of ODEs derived from PDEs, I recommend using a stiff solver, in particular ODE15S. So the S here means stiff. Now I've not defined what it means for a system of ODEs to be stiff yet. I will be talking about that later on in this chapter when we do convergence analysis and stability. But that's something that's a big problem. A lot of ODEs that come up in real applications, especially those coming from PDEs, have this problem of what's known as stiffness. So certain specialized methods have to be used for them. Something like Euler's method is definitely not going to cut it. Okay. So here we just saw a first order method. I'll start talking about higher order methods, such as rugged cutter methods, which you might have heard of on Monday. In the meantime, are there any homework questions, anything like that? Well, okay then. And we're done.